Assalamualaikum warahmatullahi wabarakatuh. Okay, today I would like to do some revision on atomic emission spectroscopy. Okay, this topic actually, if you still remember, we have covered a week before the MCO. Okay, first I would like to start on the principle. Okay, when we talk about atomic emission spectroscopy, basically, these are the technique that can be used either to determine the amount of the target analyte in a sample, basically for the quantitative purpose, or it also can be used for the qualitative. Okay, if you look into this slide, first, in here we have thermal, electrical and chemical energy. These are the examples of way how we can generate or produce radiation or electromagnetic radiation. So let's say, when we apply and some electrical energy, and then there's a radiation being emitted and directed into the sample. This sample will absorb the radiation and causing, because in this slide we focus about atom. So when the atom absorb the radiation, it will undergo excitation. So it excite or move from electronic at the ground state to the electronic at the excited state. It can the excited state, it can go at the this is electronic of these two is the electronic state at the excited state, but the one at number 2, the energy is higher than number 1. The more radiation be absorbed, this atom will excite to the higher electronic state. So this one actually, this arrow explain the phenomenon for the absorption process. Because the atom at the excited state is not stable, because the excited state is not stable. At some time, the atom will go back to the ground state. In order for it to go to the ground state, it must release the energy. So by releasing energy, by producing radiation, we call emission radiation. So these are the phenomenon in atomic emission spectroscopy. So this one explain for the emission process. So radiation that being emitted, let's say in this slide, there's a 3 arrow here. The one, the arrow with the longer dimension, which is in here, represent wavelength at this position. Because the direction of the wavelength, it goes towards right side. The value for the wavelength is longer. From Planck equation, we know that the wavelength, the relation between wavelength energy is indirectly proportional. That means higher energy, shorter wavelength. And for this one, it represent this wavelength represent the one with the lowest energy, which is this one. So so this one we call, this graph or image here we call a spectrum. Okay, you have to remember a spectrum. The y-axis will represent the amount of radiation that involved in the interaction with the analyte. With the x-axis plot in wavelength unit. Okay, so in this case, the y-axis in here represent the intensity of radiation that being emitted by the excited atom when it want to return to the ground state. Okay, one thing you need to remember, okay, because an atom, okay, it consists nucleus, and we also expect in atom there are several suborbitals. Okay, so the suborbital, the outer suborbital, let's say in here, okay, represent the highest electronic energy. Okay, so if you want to represent what happened, okay, if you want to show in graphical form, okay, what happened to the electron inside the atom that causing the emission of photon. Okay, the direction must be from outside to inside. That means from the outer to the inner orbital. The movement of electron from the outer orbital into the inner orbital, which represent from the highest energy to the lowest energy, okay, will associate with emission of photon. Okay, for the absorption, the direction is opposite. Okay, when the electron move from the inner to the outer, that means the electron move from the lower energy to the higher electronic energy. It will involve absorption of photon. Okay. What we expect? Okay. Okay. Again, when intensity plot as a function of wavelength, we call this as a spectrum. Okay, because in atomic emission spectroscopy, okay, each of this one actually each of this line represent the radiation, electromagnetic radiation that emitted at a particular wavelength. So this spectrum, okay, the spectrum that come up from the AES, we call a line spectrum or spectral line. Okay, because each of the radiation can be distinct clearly, okay, or can be differentiate clearly. Okay. Okay, so this intensity value are important for the qualitative, because from the intensity we can relate with the concentration using the Beer's law, and then we can know, okay, actually the intensity that we intensity of radiation that emitted that we measured from a sample actually equivalent to what concentration, okay, of the analyte in the sample. Okay, beside of using for the quantitative, okay, each of the radiation that emitted, okay, at this particular wavelength, actually we can use relatively for qualitative analysis. Okay, what it tells you basically, each atom, okay, when it move from one orbitals to another orbitals, okay, it require certain energy, okay. So this value and it, for example, okay, for aluminium, let's say for aluminium, aluminium, the resonance line for aluminium Okay, resonant. I hope you understand what I mean resonant line. Okay, so the resonant line for the aluminium, the wavelength where the maximum intensity were observed. Okay, for example, like 260 nanometer. Okay, at 260 nanometer is same. Okay, when we measured the resonant line for the aluminium from sample food, from sample rocks, from sample water. Okay, because the value does not change. Okay, that means we can use the wavelength, okay, value to get some idea. Actually, this one from this wavelength actually represent what kind of element. Is it aluminium? Is it iron? But okay, but when they compare, basically the instrument, they have the database, okay, the collections for aluminium, what the wavelength where the maximum intensity are observed. For iron, what wavelength the maximum intensity was observed. So they have put the information in the database. So from there, using the database, okay, when we analyze the sample, we can get idea, okay, based on the wavelength value, actually it represent what element. Okay, okay. Now we go to the okay. That's the okay. Just now when I mentioned, that's the principles of atomic emission spectroscopy. Okay, so okay, okay. Now we go to the what factor, okay, that we can, okay, basically in AES, how many types there are. So we can divide, okay, the atomic emission spectroscopic technique into two. Okay, when we divide this into two, basically we divide, or we classify, or we categorize based on the excitation source that used. Okay, for example, in flame AES, okay, in flame AES, flame is the one that responsible as the excitation source. In plasma AES, okay, in plasma AES, plasma is the one that responsible, the one that play a role as the excitation source. Okay, what do we mean by excitation source? Excitation source is okay, is responsible for causing the target analyte or target element to be excited, or we can say to move from ground state to excited state. Okay, that means from E0 to E1, E0 to E2, E0 to E3. Okay, it doesn't matter as long, okay, what component that responsible of causing the target element to be excited, that means to move from the ground from the electronic ground state to the electronic at the higher state, is flame and plasma. Okay, if you look into this slide, you know already, okay, the flame has different function in atomic emission and atomic absorption. Okay, for example, in atomic emission, okay, flame not only as a excitation source, it also as the what? Okay, so this one work as a excitation, okay, it cause, okay, it undergo excitation process. Okay, in this case, the flame, okay, act as the excitation source. That means we did not need the radiation source. In here, flame, okay, not okay, let me rephrase again. Okay, in this slide you can see that, okay, for the atomic emission, flame has two functions. Okay, first as the excitation source. Okay, because it works as an excitation source, we does not need radiation source like we need in atomic absorption. Okay, another function is flame work as an atomizer, similarly as flame work in atomic absorption. Okay, okay. Now, one thing you have to remember also, in atomic absorption, the intensity of radiation being emitted, okay, that measured in the y-axis here, okay, is depending on the population of atom, okay, in the excited state. Okay, sorry, okay, but okay, in atomic absorption, okay, in y-axis, the intensity of radiation that being absorbed is depending on the populations of atom at the ground state. Okay, so in AES and AES, both the signals in the y-axis are depending in different situation. That means one depending on the population at the ground state, another one depending on the population of the atom at the excited state. Okay, so I just would like to simplify about the Boltzmann equation. Okay, so the Boltzmann equation can be used to determine how much for atom, let's say for any atom, okay, for any atom we can calculate the population of the atom between the ground state and the excited state. So all atoms, okay, when you go through the Boltzmann equation, we find that, okay, the population of atom mostly are present in the ground state, where it represents about 99.98%, okay, in the ground state, while the remaining will be in the excited state. And this explains why the AES is preferable for analysis for most element compared for AES, okay, except, okay, when we deal with non-metal, metalloids and alkali metals, okay, or forbidden transition metal. Okay, so okay, that's all for this video. Okay, see you shortly later. Bye.